The relationship between exponential form and logarithmic form is given below. This is a two-headed arrow because this is a two-way street from one form to the other. Exponential form is the easier one to recognize because we're used to raising a number to a power and getting some kind of value. For example, 2 to the fourth power, if you multiply 4 2's together, you get a product of 16. What's not easy is writing that same information in logarithmic form. So if you take 2 to the fourth equals 16, and you write that in logarithmic form, your log has a base b. In our case, that will be a 2. Our numerical value overall was 16, so that's why the 16 comes next. And then our exponent was 4. So the way to read this is log base 2 of 16 equals 4, but what's easier to understand is 2 to the fourth power equals 16. There are two different ways to write the same information. Writing 2 to the fifth as 32, if we multiply 5 2's together, our product is 32. In logarithmic form, that gives us log, our base number is 2, our overall value is 32, and our exponent is 5. So log base 2 of 32 is 5. 5 is the exponent required to change 2 to 32. Find the value of each logarithm. Our first logarithm, we have log base 2 of 8. Now, since logarithms are really just finding the exponent, I'm going to set this equal to x. Translating, 2 to the x power equals 8. And like our last video, we learned to rewrite these equations with the same base number. 8 is 2 cubed. So if our base numbers match, then our exponents have to be equal. There will be times when we can't write each side with the same base, and we'll use what's called change of base to reroute our problem so we can still solve it. Middle example, log base 3 of 3. Set that equal to x because we're looking for the power of 3 that's equal to 3. Well, since 3 can be written as 3 to the first power, we know x has to be 1. And then finally, on the far right side, at the bottom right, we have log base 7 of 1 equals to, turns out it's 0. 7 to the x power equals 1 after we translate. 1 you can write as a positive number to the 0. We need to use a 7 to get our bases to match. But once we write 1 as 7 to the 0 power, we have matching bases, so x has to be 0. One-to-one property also extends to logarithms. Our first example, we have log base 3 of x minus 4 equals log base 3 of 1. Just like our problems at the top and on our last video, if you have matching bases, you can set the exponents equal. Same thing with our logarithms. If our logarithms match, you can set the parts behind each one equal. X minus 4 equals 1 when x equals 5. The example to the right, if you do not see a base number written under log, it's an understood 10. Just like with square roots, you don't have to write the 2 to indicate it's a square root. The same thing with logs. If you don't have a base number written, it's an automatic 10. And it's okay to write in a 10 if you need to. Since we have matching logs, we take x squared plus 5x and set that equal to 24. Subtract 24 from both sides, and that will give us x squared plus 5x minus 24 equals 0. Factoring, we use a positive 8 and a negative 3. The first factor is 0 when x equals negative 8. The second factor is 0 when x equals 3. With logarithms, you have to check to make sure that when an answer is substituted in, you don't get 0 or a negative. Let's check negative 8. Negative 8 squared is 64. 5 times negative 8, that's negative 40. 64 minus 40 is a positive 24. that works. 3 is the same way. 3 squared plus 5 times 3, 9 plus 15 is also 24. If you happen to get an answer that when substituted in gives you a negative value or 0, you throw it away. As long as that doesn't happen, you keep your answer. Sketch the graphs of 3 to the x power and log base 3 of x. Exponentials and logarithms are inverses of one another provided their base numbers match. 3 to the x, from our last video, we know that looks like this particular graph. 3 to the 0 is 1, 3 to the first is 3, and 3 squared is 9. So that gives us some points to draw a curve through. This is our graph of 3 to the x. The inverse, remember, it's a mirrored reflection across y equals x. We also know that intercepts change. A y-intercept on one function becomes the x-intercept of the other. Asymptotes, this one has a horizontal asymptote at y equals 0, so the inverse will have an vertical asymptote of x equals 0. Switching our points around, 0, 1, if you transpose those numbers, you get 1, 0. We also have 1, 3. If you flip that, that's 3, 1. And finally, 2, 9 transposed is 9, 2. Draw a reflective curve, and you will notice there's beautiful symmetry between an exponential and a logarithmic graph, provided their bases are the same. I'm going to shrink this down. We've got some questions to answer. The first one is domain and range. In our exponential function, because you can raise 3 to a negative power, a 0 power, or a positive power, your domain is all real numbers. 3 can be raised to any number. The answer you get, however, will always be positive. No matter how hard you try, 3 to the x will never give you 0 as an answer or a negative as an answer. So its range is only the positive numbers. The logarithm will be totally opposite. Its domain is only positive numbers, because when you type in log or hit the log button, if you type in a 0 afterwards or a negative, you get an error. It's a domain error. Logarithms are only defined for positives. So the domain of a logarithm is positive numbers. The range or answers you get make up the whole gamut of real numbers. You can have negative y's, you can have a 0 y, and you can have positive y's. But you can only enter positive numbers into the function. The answers will cover all signs and 0. Intercepts, that will be next. Our exponential function has a y-intercept at 0, 1. It does not have an x-intercept, does not exist. G of x, which was our logarithmic function, it has an x-intercept at 1, 0, but no y-intercept. See how these are reversed? That's true with all inverse functions. And then finally, as I mentioned earlier, vertical and horizontal asymptotes. The exponential function, there's no vertical asymptote, but there is a horizontal asymptote at y equals 0. As x gets extremely small, your function takes on smaller and smaller values approaching 0. With a logarithmic function, you have a vertical asymptote because your x values can get really close to 0 without actually being 0. There is no horizontal asymptote. As the graph goes out, as x's get larger, the answers get larger. Very similar example, we're going to use the function e to the x plus 3 for our exponential example. And natural log of x minus 3, as its inverse function. A base number of e and a natural log, that's a log base e, will be inverses of one another. E to the x plus 3, adding 3 to the end shifts your horizontal asymptote from the x-axis to y equals 3. So your graph will be flat until it explodes. Now there is no vertical asymptote, so I've stopped these dashed vertical lines on purpose. I don't want you to think there's a vertical asymptote at 3. Now there is for the logarithmic function, because remember, natural log or any logarithm has to be positive. X minus 3 is positive as long as you're larger than 3 with x's. So that's a vertical asymptote of x equals 3 for that logarithmic function. I stopped the horizontal asymptote, the dashed lines, I stopped it short because there is no horizontal asymptote for the logarithms, only a vertical asymptote. Domain and range. For your exponential function, because your x's can be negative, 0, or positive, domain's all real numbers. The answers or y values that this function produces are only values greater than 3. Range is all numbers greater than 3. Switching to the logarithmic function, natural log of x minus 3, the domain is numbers larger than 3, so 3 to infinity. The range covers all y's, negatives, zeros, and positives, so your range is all real numbers. The x and y intercepts for the exponential function, there's a y-intercept at 0, 4. There is no x-intercept. For the logarithmic function, there's an x-intercept at 4, but there's no y-intercept. I've already labeled the asymptotes for the exponential function. There's a horizontal asymptote of y equals 3. For the logarithmic function, there's a vertical asymptote of x equals 3. And so down at the very bottom of your screen, these asymptotes are for the exponential graph, e to the x plus 3. These asymptotes are for the logarithmic function, natural log of x minus 3. Some quick notes. Common logarithms are written as log x. You won't see a base number specifically written, but it is totally okay to write a 10 there if you need it. Its inverse is 10 to the x. Natural logarithm, written with ln x, is the inverse of e to the x. A natural log is the same as log base e. But we just, as mathematicians, we don't write log base e, we shortened it up to ln. So log base e of x is the same as natural log of x. And again, common log, it has a base number of 10 that just isn't written, like the 2 on a square root. The one-to-one property applies to natural logarithms just as much as they do to any other logarithm, whether it's common or a base of 3 or 5 or whatever number you wanted to sub in. Use the one-to-one property to solve each equation. In our first example, natural log of x plus 7 equals natural log of 7. Same logarithm, x plus 7 has to equal 7, and that's true when x equals 0. Natural log of x minus 2 equals 7 when x minus 2 equals 7, and that's true when x equals 9. Again, I do want to warn you, sometimes when you solve these, you get an answer that when substituted in cannot be used. For example, if the answer down here happened to be like a 0, x equals 0, you couldn't use it because 0 minus 2 is negative. You also couldn't use just straight up 2 because 2 minus 2 is 0. Logarithms require positive only.